The universe is vast, filled with wonders that defy our everyday imagination. We see stars glitter in the night sky, distant galaxies swirl in beautiful spirals, and planets orbit their suns in a predictable cosmic dance. But among all these celestial marvels, there is one object so strange, so powerful, that it pushes the very laws of physics to their absolute limit. This object is a black hole. It is a place where gravity is so intense that nothing, not even light, can escape its grasp. It is the ultimate cosmic trap, a one-way ticket to a destination from which there is no return. What would happen if you were to take that journey? What would you experience if you found yourself falling into one of these gravitational monsters? This is not just a question for science fiction. It is a genuine scientific inquiry, one that has captivated physicists for decades. The journey into a black hole represents the most extreme physical experience imaginable. It is a voyage to the edge of reality itself, where space and time warp and break in ways that seem impossible. To understand this journey, we must venture into the heart of Albert Einstein's theories of relativity and explore the most violent forces in the cosmos. It is a thought experiment that forces us to confront the true nature of gravity and the fundamental structure of the universe we inhabit. The answer is both terrifying and utterly fascinating, revealing a process so bizarre it has been given a rather curious name. Imagine yourself in a spaceship, drifting through the silent, cold expanse of space. The strange fate that awaits you has a wonderfully descriptive, if slightly unsettling, name: spaghettification. It sounds like something you might find on a menu in an Italian restaurant in space, but the reality is far more profound. The term was coined by scientists to describe exactly what would happen to an object or a person as it falls into a black hole. It is the process of being stretched vertically and compressed horizontally, much like dough being rolled and pulled into a long, thin strand of spaghetti. On Earth, we see the effect of tidal forces most clearly in our oceans. The moon's gravity pulls on the Earth, and it pulls more strongly on the side of the Earth closer to it than on the side farther away. This difference in gravitational pull creates a bulge in the oceans on both the near and far sides of our planet. As the Earth rotates, these bulges create the familiar rhythm of high and low tides. Tidal forces are not unique to the Earth-Moon system. They are a universal consequence of gravity. Jupiter's immense gravity creates powerful tidal forces that flex and heat its moons, leading to incredible volcanic activity on Io. Even our own bodies exert tiny tidal forces on each other, though they are far too weak to ever notice. A tidal force is simply what we call the difference in the strength of gravity across an object. The reason tidal forces become so incredibly powerful near a black hole is due to the extreme steepness of its gravitational field. Near a black hole, however, the gravitational pull increases at a staggering rate as you approach the singularity. The difference in the force of gravity between your head and your feet, even over the small distance of your own height, would grow from negligible to immense in a very short amount of time. Spaghettification. Imagine you are falling towards a black hole, feet first. This means the gravitational pull on your feet will always be stronger than the gravitational pull on your head. This is the vertical component of spaghettification. This results in a powerful horizontal compression. This combination of stretching and squeezing is the essence of spaghettification. To make this clearer, let us follow the journey of a hypothetical astronaut. Let's call her Amelia, as she makes the ultimate sacrifice for science. At first, far from the black hole, she feels nothing but the familiar sensation of weightlessness. But as she drifts closer, the subtle effects of the tidal forces begin to manifest. As Amelia gets closer, this gentle pull intensifies. The discomfort would grow into pain as the forces begin to overwhelm the structural integrity of her body. Soon the stretching force would become immense. Her bones would begin to crack and break under the strain. The forces would keep pulling, stronger and stronger, until even the atoms themselves are ripped apart. Amelia, our brave astronaut, would be transformed into a thin, glowing stream of subatomic particles. So what exactly is a black hole? In the simplest terms, it's a region in space-time where gravity is so incredibly strong that nothing can escape from it, and not even the fastest thing in the universe, light. This is why they're called black holes. They do not emit or reflect any light, making them completely invisible to our eyes and telescopes in the traditional sense. Albert Einstein. Before him, the scientific world saw gravity as Isaac Newton did. In 1915, Einstein unveiled his theory of general relativity. Einstein proposed a revolutionary idea. He said that gravity is not a force at all. Instead, it is a consequence of the way mass and energy curve and warp the very fabric of the cosmos. For decades, black holes remained purely theoretical objects. How do you find something that is perfectly black and emits no light? Well, the answer was to look not for the black hole itself, but for the effects of its immense gravity on the space and matter around it. One of the first major breakthroughs came from the study of binary star systems. Astronomers found a system called Cygnus X1. But the most direct and spectacular confirmation of Einstein's theory came in 2015. Scientists at the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected something extraordinary. Gravitational waves. The signal they detected was the echo of two black holes spiraling into each other and merging in a distant galaxy over 1 billion years ago. We heard the sound of them shaking the universe. But in recent years, thanks to powerful new telescopes, can we actually see this cosmic stretching and shredding happen? But we can see something much larger meet the same fate, a star. It is called a tidal disruption event, or TDE, that the star is completely ripped apart. The star is shredded into a long, thin streamer of superheated gas, forming a brilliant, swirling disk of material around it. This sudden, bright flare of light is the cosmic scream that signals a star has just been spaghettified. These observations are no longer just theory. Our journey into the heart of a black hole reveals a universe that is far stranger and more magnificent than our everyday intuition can grasp. We have seen how a single fundamental principle, gravity, can manifest in such profoundly different ways. The same force that causes the gentle rise and fall of our oceans is, in its most extreme form, capable of shredding a sun. The tale of falling into a black hole is a testament to the predictive power of science. It all began in the mind of Albert Einstein. For decades, they were mathematical ghosts. We have confirmed that these bizarre objects are undeniably real. It reinforces a profound truth. The universe operates on a set of consistent rules, a reminder that even the most chaotic events are underpinned by an elegant mathematical order. Why does any of this matter? The answer is that these cosmic laboratories push our understanding to the breaking point, and it is at these breaking points that new discoveries are made. Is where our two great theories of the universe, general relativity and quantum mechanics, collide and fail. And to seek a more unified theory of physics, often called a theory of quantum gravity. The tidal disruption events that we witness are part of a grand cycle of cosmic recycling. We are, in a very real sense, connected to these distant violent phenomena. In the end, the story of falling into a black hole is a story about the power of human imagination. But through the language of mathematics and the tools of science, we can journey there in our minds. This intellectual voyage expands our perspective, reminding us of the scale and wonder of the cosmos. It fosters a sense of awe and humility, showing us that even in the face of the most destructive forces imaginable, there is a profound beauty and a deep, underlying logic waiting to be discovered. The universe is full of wonders, and the quest to understand them is humanity's greatest adventure.